All right, let's do a normal distribution problem. And then right after, we'll do a sampling distribution problem. And the word problem will have the same situation. So here's a word problem. It says a $5 bill will have an average lifespan of 4.9 years and a standard deviation of 1.2 years. How likely are you to choose a $5 bill at random that is less than 4 years old? That's a lot of words. There's a lot of numbers here. So if you had access to $5 bills, how likely is it that you're going to choose a bill, a $5 bill, that is less than 4 years old? And yes, this type of question is silly, but would you want to know something like that? Well, dollar bills tend to have a certain lifespan. And here it says that on average, they last 5 years. $5 bills don't last very long. $100 bills last longer, so do 20s. Why? Not a lot of people carry $100 bills. $1 bills are probably the ones that don't last that long. But anyway, the thing is that if you, for some weird situation, you're able to choose at random a whole bunch of different $5 bills, what is the chance that your bill will be less than 4 years old? Well, we can figure that out. The first thing we need to do is to identify the random variable. And the random variable just basically describes what you're trying to look for. Random variables are placeholders of values. Okay? And here it says, let x equal the lifespan of a $5 bill. Lifespan in years. So x could be 4 years, 10 years, 2 years. Okay? It's years. Years of what? Years of the lifespan of a $5 bill. Okay. Next thing we need to do is to draw our normal distribution. And the problem most likely will say, hey, this is a normal distribution problem, okay, somewhere. All right, another thing too, again, we need to write out the spread of the data. And we have the mean, which is 4.9, and then the spread, how are the values distributed from the mean, and that's 1.2. So you add 1.2 gives you 6.1. Add another 1.2 gives you 7.3. This is how the data is spread out. This is 1 standard deviation. This is 2 standard deviations. And you can also do it the other way. You have 1 standard deviation below the mean, 2 standard deviations. How do I get 1 standard deviation below the mean? 4.9 subtract 1.2. That gives you what? 3.7. Okay. The great thing about the standard deviation is that it gives you a story of how the data spread out. And as you know, the normal is a bell-shaped curve. You can see that not many bills are over here. How do I know that? That there are not many bills at 7.3 years. Well, the height is kind of like a frequency. It kind of is. So this height tells me the higher it is, the more likely you'll find that value. 4.9 is the average. And that's where most of the bills are. You won't find too many bills at 2.5 years, nor will you find too many bills at 7.3 years. But doing these problems, we're not looking for one particular value. We're looking for a range of values, and that is, in this case, less than 4. All the values less than 4. Another thing about this normal distribution, we have to think about the empirical rule. Well, this is a version of it. This is not the empirical rule. But what I'm going to do is these regions, I can place a probability. You know, how likely is it that I'm going to choose this area? Well, what you can do with the empirical rule is that you can figure out sections of your normal distribution, right? Think of the normal distribution as some type of, you ever had one of those pizzas where it's all rolled up, those calzones? Well, let's pretend that that was one, right? Rolled up. And if you eat this portion right here, that's 13.5%. 13.5% of this calzone. Well, it's not a calzone, it's the normal. If you ate this much, which is the bulk of it, that would be 68%. How do I know that? 34 plus 34 is 68. So that's what we're looking for. We're looking for the shaded region for these word problems. Okay, so what are we looking for? We're looking for the probability that x is less than 4. What's x? The lifespan of a $5 bill. How do I know it's less than and not greater than? Well, think of it this way. Look at the inequality and see where it's pointing. Which way is this one pointing towards? To the left. If it's pointing to the left, that means less. If it's pointing to the right, it's greater than, more. Okay? If you have another way of doing that, that's fine. Anyway, it says less than. That's why it's pointing less. Okay? All the numbers that are less, smaller, all the numbers that are smaller than 4, those numbers are what? 3.7, 2.5, and it keeps on going to infinity. So, one thing that we need to know is the area under the curve. This area under the curve will give us the probability or our answer, you know? What chance is it that we're going to get a bill, a $5 bill, that's less than 4 years old? This picture will tell us that. So 4 is right here, right? And that might not be a great placement of 4. It's probably not there. It's probably a little more closer. But we'll say it's there. And I'll say, well, that's 10% right there. This is 10%. Okay? If you say 9%, 15%, that's okay. But we know that this is not 34% because it's not all of it. And it's not 30% either. Is it 5%? I don't know about that. Okay, we got to kind of guess right. Then, do we stop there? Does the problem say it goes from 3.7 to 4? No. It says all the values below 4. So we keep on shading. Another 13.5. From here to here is 13.5. How do I know that? Because of the empirical rule. These numbers are always going to be with you. Okay? And these are estimates. Your teacher might disagree about these values. They might be, the values there might be a little bit more accurate, but these are good numbers. Okay, and then we got to shade the rest all the way to infinity. All the way to infinity is 2.5%. So if I added all these pieces, right, it's not half. It's less than half. It's 26%. That's my estimate. Okay, all right, that's my estimate. Some teachers will ask you for the estimate, others won't. Okay, but it's good to have an estimate. It gives you an idea of what you're doing. Now, you can go to your, in the back of the book and look at your standard normal table. If you have one of those, use those. But if you have a calculator like a TI-83, 84, then you can use the normal CDF function. It's under what? Second vars. The second button in the vars button. You'll find normal CDF. You need a lower bound, comma, upper bound, comma, the mean and the standard deviation. You're going to need these values. Lower bound just means what's the lowest value. Lowest value is negative infinity. Negative infinity in the calculator is represented by E. And that is above the comma. So it's the blue button, the second comma. Okay. And then you type 99. Then the upper bound. What's the biggest number? 4 is the biggest number. Comma. We need the mean, 4.9. What's standard deviation? 1.2. 4.9 and 1.2 is very important because the calculator needs to know how much of a spread is the data. And the first two numbers tell you, it's telling the calculator, this is what I want to find. And so you type it in, you enter these values, and you get 0.2266. Okay? And there's more numbers to it, of course. And then you should write your sentence. There is a 22.66% chance that you will choose a $5 bill at random that is less than 4 years old. So, think about this. If you can choose a $5 bill at random, let's say there's a whole bunch of them somewhere, you choose one of those bills, there's a 22.66% chance that you will find a bill that's less than 4 years old. Question is that a big chance or a small chance? Well, think of it this way, right? Let's say it's 23% chance, right? We'll round it up, 23. So that means there's a 77% chance. So I subtracted 23 from 100. 77% chance that you will not find a bill, a $5 bill that's less than 4 years old. You see, this whole empty spot says that, there are no bills less than 4. There are bills that are almost 5, 6.1, 7.3 years old. So you can think of it that way too, okay? Again, depending on the field that you're in, 22.66% might be large or small. Okay, let's move on. Now let's do a sampling distribution type problem. What would the probability of choosing 9 $5 bills at random with an average age of greater than 4.6 years old? Okay. So you have to think a little bit different about these problems, these sampling distribution problems. In this case, we're going to choose 9 $5 bills. What's so special about 9? Nothing really. There's nothing special about 9. I chose 9 because it's easy to take the square root of that number. But anyway, it could be any number. So you have to choose 9 $5 bills at random. And when you have these 9 bills, how can you describe these nine $5 bills? How can you describe them? They all have different ages, you would assume. Some of them will have 4.9 years of age, maybe 4, maybe 6.1, maybe 5, right? How can you describe all 9? You describe them by finding the sample mean. When you find the sample mean of these 9, then you can describe that set of 9. They're asking you, if you do choose 9 at random, will your average be greater than 4.6? years old. Again, it is a bit silly, but think about it. How do you describe what thing in statistics, right? What statistic is really the question. Can you utilize or think of when you have 9 things? You can find the average of those 9 things. In this case, the average of how old they are. And based on that, we can figure out some other things. So we're going to have to erase this because we're going to have to have a new normal distribution, not based on a bill, right? A bill, but we have to do it for 9. Now the random variable is going to change. This is the random variable. Okay, so one thing about sampling distribution problems, these group problems, is that we have a new spread. This is really the big difference between these two problems. We have a new spread. The spread means how far apart are you from the center, right? When you collect data, how far apart are these data points? The only way you can discover that is through the standard deviation, population standard deviation. Okay, so the center, the mean, is the same as the original problem. That doesn't change. The thing that changes is the spread. And after the video, I might talk a little bit about why. But we have a new formula, sigma x bar. This x bar tells me it's the standard deviation of these 9, the true standard deviation of 9. And in this word problem, we will assume that it's 1.2. Okay, sigma is 1.2 divided by the square root of n. And the square root of n is 9. Square root of 9 is 3. 1.2 divided by 3 is 0.4. So this new standard deviation of 0.4 is going to be utilized to determine the spread for a group of 9. A couple of things, just in case you are at a different point in your stats class. Sometimes they'll call this the standard error. Sigma is replaced with S, okay? And that's a whole different type of problem using the t distribution. Okay, but in this case, we're assuming this formula for groups. We need sigma. We'll assume it's 1.2, and n is 9, and so forth. We have a new standard deviation. So what we're going to do is we have our new random variable x bar. And now we have a mean of 4.9, and now we're going to add 0.4, right, to 4.9 to give you 5.3, and another 0.4 to give me 5.7. 1 standard deviation, 2 standard deviations. And then 1 standard deviation below, subtract 0.4 from 4.9 is 4.5, and then subtract another 0.4 from 4.5, gives you 4.1. So here your 1 standard deviation below, 2 standard deviations below. Gives me the spread. You can see that these values are definitely more closer to each other than the original problem. There's a reason why. That has to do with the central limit theorem, and I'll talk a little bit about that in the end. But for right now, the random variable is for groups. The way we can, one of the properties of these groups is the mean, the sample mean. And the sample mean and the mean are the same in this case. Okay, now what do we want? It says an average age of greater than 4.6. An average grade, because that describes the property of 9 of these bills, right? We can't have all these 9 bills individually. These 9 bills, we need to collectively put them together and describe them with one number. And that's the mean of those 9. And we have to do it as greater than is going to the right of what? 4.6. So because we have a new random variable, meaning it describes what we're talking about, which is a group, in this case 9 bills, let's find out where 4.6 is. It's right there. And we shade that little piece, 4.6, all the way up to there. I'll say it's 25% to here. Why do I say it's 25%? Because from here to here is 34. And I'm thinking I'm shading a little more than half. Half is 17. If you said 21%, that's cool. You said 30%, sure, why not? What about if you said 45%? No, because from here to here is 34. Okay, you gotta be reasonable. All right, 25, and then the rest is half, right? So 50%. So altogether is 75%. This whole thing is 75%. This is an estimate, just like we estimated here. Again, depending on your teacher. If your teacher says, give me an estimate, then that's the answer. If you need to continue to get the more accurate answer, the answer from the standard normal table or your calculator, let's do it. Now, if you have a standard normal table or Z table, then utilize your Z table. Here we're going to do the calculator. We're going to go with normal CDF. We're going to go with the lower bound or the lowest value from where it's shaded. It's right here, 4.6. The lower bound is the lowest part, right? The lowest value when you started shading. What else? We're going to also need the upper bound. This one, the upper bound, meaning the largest value, which is infinity, because this goes on forever. Infinity, and the calculator is E99. Okay? Then you're going to need the mean, population mean, 4.9, and the new standard deviation for the group. Some books will call it the standard error. Okay. Now we have a new value. We have 0.77337. So there is a 77.34% chance of choosing 9 $5 bills at random with an average age greater than 4.6 years old. You can see it in the picture. You can see that we're looking for a group of 9 bills that are more than 4.6. Well, 4.9 and above, that's half. Half of all bills out there are 4.9. And you want more than 4.6. So even another little piece right here. So it's likely that when you choose 9 $5 bills at random, when you find out how old they are and you look up the average, they'll have, most likely, you'll choose a group of 9. What type of chance? 77.34% chance, which is pretty high. I estimated at 75%. Okay, so these problems are different in one respect, and that is the spread. But there is this thing called the central limit theorem that the central limit theorem allows you to have this assumption of having a new spread. Okay, so that's it. We're done with the problem, but I'm going to talk just a little bit about why are these values smaller than the original? Why is the sampling distribution spread smaller than the original problem? If you think about it, in the original problem, where you have a random variable x, most values, 68% of the values actually, are from 3.7 to 6.1. 68% of the values. Most likely a bill will be right here. A $5 bill will be right here. Okay? Most likely. Again, most likely a $5 bill will be between here and here, because that's the meat and potatoes of the distribution. 68%. That's 70%. So if you think about it, when you're choosing 9 $5 bills, you'll find one over here, one over here, one over here, one over here. Maybe you'll find one over here, one over here, one over here. 1, 2, 3, 4, 5, 6, 7, 9, right? Most of them will be right here. Not over here, not over here. Yeah, random, you'll choose them from there. So, most of the bills will come up in this little area. How much? Well, let's see. It goes from 4.1 to 5.7. 4.1 is over here somewhere in the original distribution, in the original distribution, the normal distribution, from 4.1 to 5.7, which is here. This little region right here is when we're talking about groups, a group of 9. Why? Because most of your values should be coming from there. And thus, because most of your values are coming from there. Why are most of your values coming from there? Again, it's the frequency, right? There are not many, let's do this blue. There are not many $5 bills that are over here, not many $5 that are here, not many $5 that are here or here. But there are many $5 bills that are coming here from the middle, the average. The average is the balance point. The average is where the action is happening. The average is where most of the things are occurring. And the spread from the average is narrow for groups. It's narrow. And because it's narrow, we're pinpointing more, the probabilities are more narrow too, because we are getting a group instead of an individual. A little bit hard to explain, a bit. Definitely looking at the central limit theorem in your textbook will give you a different explanation. This is not really the definition or the explanation of the central limit theorem, but this is kind of like the cause from it. Okay. But anyway, go ahead and look at this, and hopefully this will give you a better understanding of how to do these problems.